Good evening, everybody. This is presentation by HSA, Rafik, Viswak, and Weian from HSA. We're also joined by John Wallace, professor of structural concrete at UCLA. I want to ask a question before I start. How many in the room are practicing structural engineers? All right. So for those who are not, I think we're going to get you a real life flavor of what's happening out there. So ask a lot of questions. I think it's a very practical presentation. To put things in perspective, HSA is one of the premier structural offices in Southern California. We specialize in big boxes, a lot of retail boxes, logistics centers. We put about 300 of those buildings a year. About 100 plus of those are in seismic zones. And the question we're going to try to answer today is, do we need to do the picture on the right or the picture on the left? If you look at those two pictures, the picture on the right is really what we want to build, and we feel it's right. The picture on the left is what ACI 318 would ask you to do. Very intense. Again, same question here. The picture on the right is what we would like to build, what we feel is appropriate. The picture on the left, with all those intense cross ties at 2.5 inches on center, is what ACI 318 is asking us to do. So my colleagues Viswak and Weian is going to walk you through the process. We did a code design and we did a performance-based design using ESE 421 and ECI 369 to demonstrate that all this excessive detailing is not required. And at the end of the talk, I'd like to collect your thoughts and get your input as well. Weian, the floor is yours.
Thank you, Rafik. So I'm going to start off to introducing the two-top constructions, first of all. So two-top construction is a simple and then the box-shaped structure. It is composed of several, concrete panels around the perimeter that's being constructed, irregular panels. So the walls, the bearing walls, and also resist a lot of force. The dimensions could vary. So this is one of the examples with 5,000 feet long and then also 400 feet wide. It could be square shape as well, which is 700 by 700. So really the dimension really changes. So one thing about the construction is we have several different panels and can withstand the size. The panel look in the short directions. One typical panel is a solid panel, 26 foot wide and 40 to 60 feet tall. The other panels on the wrong direction with two big openings of we call dog doors is 9 foot wide with 10 foot tall. Leave like 2 feet, 4 feet, and 2 feet piers. So we have designed that to when subject the earthquake load. The other unique feature about this building, it is a flexible diaphragm with light, that load, and the diaphragm could be plywood, wood deck, or metal deck. Because during the earthquake, the fractional deck is more than half, twice of the wall, so caused by the flexible diaphragm per ASC 7. To determine the seismic weight, actually, look at this load path. So the load coming from the panels in other directions, coming autoplane, plus the force from the diaphragm, and that will give you the shear force, which you need to utilize to determine the shear force in the walls on top and the bottom. So really effective weight is combining these two. Then effective seismic weight roughly is 18 to 50 PSF. Now let's compare two different constructions. One is two-top building with concrete wall, and the one is 4-story office building using a concrete tower as lateral force. Let's use the concrete two-top building as the baseline case. So you can see, for office building, effective seismic at each level about 3 to 9 times more than, the logistics center. We have 4-story above, and the shear wall length is about 1/4 compared with, around the perimeter of the two-top building. So totally seismic is about 50 to 150. And if you look comparing this shear per unit length, it's about 45 to 100. So you can see, load to the, warehouse wall is much lighter compared with office building. Now let's take a look at the historic performance of the wall and the building under earthquakes. Never we seen an issue for the wall fails in plane. One issue we find out is separation between panels and roof. And that's due to inadequacy of the wall ties. And then the wall ties the functions of the wall ties have been developed over the years. And it's being adopted by UBC 94 and then including UBC 97 to current code. Another issue for this panel is moving an outer plane. It's called the Bowing effect. And then Viswak did a testing on concrete hilltop walls, and they found out that the diffraction limit on the earthquake load LO150. So now let's take a look at why we see the failure mode is always separations, not really in plane fair. Why we need to look at the exact buildings, what is going on with this construction. We're looking at a building with 1 million square foot. With 1,600 long and 600 foot wide, 40 foot clear. 40 foot clear is defined from the finished floor to the bottom of the steel. We have 40 foot clear. Let's say the building has seismic category D with SDS 1.3. We're looking at two different panels, one solid located short side and dot panels located on the long side. And because the outer plane calculations, we need to use 12-inch thickness for, the short side, solid panels and dot panels 10.5 inches. So, before we do the design, we have to select appropriate seismic lateral force resisting system. Typically, industry standard go with intermediate shear wall. But for this building, and look at this, the code, they require 40 feet, the height of 40 feet. But, and there's a footnote for I saying, for single-story warehouse can be limited to 45, can expand to 45. Now for this example, the height from the bottom footing to the average of the roof height about 50 is exceeding 45, which means we have to utilize special concrete shear wall for our system for the building. Now the next step we need to calculate what is the shear force in each wall separately. And after we do that, we need to, we need to calculate how much force will be transferred to each wall panel specifically using the rigid distribution analysis. So, from this analysis, you find out the wall in short side direction, the solid wall about 54 kips, and then 48 kips is long direction for the top panels. Now we're going to utilize this load to determine the reinforcement for current code ACI through 1819. Well, let's look at the solid wall first, right? So we have 54 kip load at the top. So, per the code, we can utilize at the minimum reinforcement, although we not use it. But let's start with uniform reinforcement to check this fractional. And then number 3 is 15 joint center. So these ratio about fractional about 0.43. Now let's load the panel outer plane because it is about a 40 foot clear. For outer plane, we need to utilize number 711 joint center. Make sure the calculation work and also the diffraction work. So see, there's a big difference here. So really the vertical rebar is driven by outer plane. Number 711 joint center. Now we put the number 711 joint center back to this in the lateral analysis to figure out this ratio is only 0.11, way less than 0.43. Now let's look at the shear demand, shear reinforcement. Now we can utilize the minimum required by ACI, number 4, 16 joint center. We calculate DC ratio about 0.21. And then, because it's special concrete shear wall, we need to provide confinement for both ends. And then we're using number 711 in center, which is exceeding the limit of ACI, which is 400 over FY. Right? So we had to provide a confinement at both ends. And to keep it in mind, number 7 is driven by the outer plane. And then we had to provide a confinement, which number 3 is 16 in center, and this provide a construction photo for this, the end of the panels, and see very heavy detailing for the code. Now this is kind of a little summary for the solid panel design. We use number 7, 11 on center, and then the horizontal number 4 is 6 on center, and number 5 panels and footing styles, and then at the ends of the panels is number 3, 6 on center, provide confinement. Now let's move on to the next panel, which is dock panel with 2 openings, leave like 2 foot pier and 2 foot pier and 4 foot pier. We have 48 kip from slightly loaded at the top, and if we load it, it has moment demand of 29 kip foot. So per ACI code, it is require at least 1% of the rebar, which is for number 5 vertical rebar. So do the calculations to figure out this ratio for the fractional and combined fractional axial about 0.17. Now let's load the panel autoplane. So this will give us the vertical rebar fly number 7 each face, which means much heavier than the in-plane design. So if we load it, if we do analysis using flight number 7, the DC rate went down to 0.1 actually. So now next thing we're going to do is we look at the transfer rebar because aspect ratio for this panel is greater than less than 2.4, which is 2.5 or 2.3. It is classified as special column. We need to follow the column detailing for all this reinforcement, which means we need to do ties at 2.5 mm center with crossbars. So here's construction flow. You see very intense rebar, transverse rebar across the boundary elements, 2.5 mm center and with crossbars. So then we check the in-plane shear. Per code, we had to use VPR, we checked the CR 0.83, and this is kind of design summary of this dock panels. We have flight number 7 each face with number 3 and 2.5 mm center with height, see very heavy detailing, and the 4 number 5 panel the footing dowels. Now this is kind of recap of the design for this building with, SDS 1.3. So the one shown on the left, it is a solid panel with number 7, 11 mm center, but it really the DC ratio to resist earthquake load only 0.11. For the solid panel, we have to use flight number 7 rebars, and DC ratio only 0.1. All the vertical rebar are driven by the outer plane, but really the in-plane demand is very low. You can see low ductility demand. And also for the code, we require really heavy detailing. Number 3, 16 mm center, and number 3 at 2.5 mm center. So really, from practice engineer point of view, really heavy wall detailing for the low ductility demand, right? So, this is something we had to think about it. So, and then my colleague Viswak will dig into this to look at the ductility demand from performance-based approach.
Thank you, Weian. We'll be using an alternate performance-based approach. So the two codes that we are using is ASC 41 and ACI 369. So in the future codes of ASC 41, it will be referring to ACI 369 for all concrete related performance standards. So that's the reason we have used ACI 369. And here is a section in ACI 369 which talks about non-conforming walls, and our proposed detailing that we are showing, it comes under a non-conforming shear wall. So these are the two requirements. So if we have a single layer or if we have less horizontal reinforcement, that comes as a non-conforming shear wall, and also if we have any missing boundary elements, it comes as a non-conforming shear wall. And this is a table from ACI 369 which gives us the M factors. Basically, it kinds of defines us the ductility of a non-conforming shear wall. So these are the three mechanisms, load mechanisms that we have utilized in calculating the load path. So the performance objective that we used are life safety for BSc 1N condition and collapse prevention at BSc 2N condition. And the code design is based on BSc 1N life safety condition. So here are some of the definitions of performance-based actions. So this is the summary slide that we had before. So the summary of the solid wall design, and based on this section of ACI 369, we can categorize the wall as flexural control. So we will check all of the shear, all of the horizontal reinforcement for force control, and the vertical reinforcement as flexural control and deformation. So here is the ASC 41 analysis that we did. The period of the building is 1.6 seconds. So based on 41 analysis, we were able to calculate the demand on the wall. Over here on the horizontal wall is around 200 kips for life safety and 400 kips for collapse prevention. So based on that horizontal reinforcement, you can see that the shear DCR is 0.15 and 0.17 for force control action. But when we look at flexural demand, based on the M factors, we can see it's very low, it's only 0.13 and 0.19. So if you use M factors as 1, you can see that the DCR has grown only a little bit more for 0.38 and 0.62. So based on this, we can say that we don't have any ductility. So this is the next load path that we went through. It's based on diaphragm yielding. So we have the Ocean factor of the diaphragm over here. Based on that, we calculated the demand coming onto the wall, assuming that we have adequate shear, adequate capacity at the support. And here is a summary of the DCRs. Again, you can see that the DCR for shear it is way lower than 1, and DCR for moment without M factors it's also much less than 1. So that means even in this load path we do not have any ductility demand. So the next approach that we are doing is we are figuring out the load at where the support will start to yield. So as you can see, for life safety and collapse prevention, we have 135 cases where support will start to yield, and for collapse prevention, it is around 170 cases. So based on this is the summary of the shear and moment DCR. So you can see this case it is much lesser than the previous two conditions. The DCR for shear is like 0.08 and 0.07, and DCR for moment it is 0.21 and 0.27 without M factor. So we do not have any ductility demand in this load path as well. So we went through the same process on a dog panel as well. So this is the table showing the M factors for column condition, for a special column condition. So on this case we have a period of 1.3 seconds. And here is the shear demand on the leg. So we can see the DCR is 0.68 and 0.79 in this case. When you look at the moment demand, it's 0.15, 0.2 with M factors, and it's only 0.39 and 0.64. And you can also see we have relaxed the tie spacing from number 3 at 2.5 to number 3 at 10. So this is all with a relaxed tie spacing. This is the next load path that we calculated with. So we have here the same thing, we are assuming adequate support. And based on this, it is the summary of shear and moment. So you can see that even with this load path, we have DCR of 0.34 and 0.45, and we don't have any ductility demand on the back. The last load path is figuring out the load where our support will start to yield. And here we have much lower DCR at 0.2 and 0.2 for life safety and collapse prevention. That means that we do not have any ductility demand. So for the proposed detailing and conclusion, Rafik would be concerned. So for the proposed detailing, so on the top, that's the current ACI detailing that we have. So for solid panels, we need to provide nominal boundary reinforcement as number 3 at 6, and for column condition, we need to do number 3 at 2.5. But you can see that what we are proposing is much lighter. We don't need to have any confinement at the end, so there is no requirement for nominal boundary, and also relax the spacing for the column over there. Instead of number 3 at 2.5, we are doing number 3 at 10. So this would give us much more relax.